Okay, a very good evening to all the attendees who have joined on the 5th day of this online Science Academies lecture workshops on frontiers in science engineering opportunities for graduates, and which is being organized by the three science academies: Indian National Science Academy, Indian Academy of Sciences, and the National Academy of Sciences, Allahabad. The convener of the program, Professor Anurag Sharma, there, and he's a GC Bose National Fellow at Department of Physics, IIT Delhi. And today we have two talks. The first one is by Professor Shrikrishna Gopalrao Dani, and who is a distinguished professor at Center for Excellence in Basic Science, University of Mumbai, Maharashtra. As a customary, I'll introduce Professor Dani, who joined the TIFR, that is Tata Institute of Fundamental Research, Mumbai, in 1969 to work under the guidance of Professor MS Raghunathan for his PhD degree awarded by University of Mumbai. He continued to be with the TIFR and held various visiting positions at different institutions, including the Institute for Advanced Study, Princeton, Yale University, University of California, Berkeley, University of Chicago, Isaac Newton Institute, and so on. He has received several awards and honors that include the SS Bhatnagar Prize, TWAS Prize in Mathematics by the Academy of Sciences for the Developing World. He is a Fellow of the Indian Academy of Sciences, Bangalore, Fellow of National Academy of Sciences, Allahabad, and has delivered invited lectures at the International Congress of Mathematicians, Zurich, in 1994. With these words, I request Professor Dani to kindly deliver his talk.
Let me begin by...
Yeah, I've just handed over to you, sir.
Thank you, Dr. Saxena, for the invitation and the kind introduction. And good evening, everyone. Welcome to this talk. And it's rather nice of you to have, to be joining this talk, which is perhaps one of the more prosaic talks from the program. But that's my subject, and that's what I should talk about. So let me begin by sharing my file. Yeah, the topic I have chosen for today is continued fraction expansions of complex numbers. Now, my sense is that most of you, or perhaps all of you, would know about complex numbers, but maybe not all of you would perhaps know what are continued fraction expansions and what they are good for and so on. So despite this composite title, I'm actually going to spend more time trying to convey what the continued fraction expansions are and why we should be interested in them, not just mathematicians, but also the scientific community and maybe people at large as well. So let's begin sort of at the beginning in some sense. So let me go to the next page. Yeah, so here is an outline of the talk. First of all, I'll recall to you how we write numbers. Writing of numbers is in fact the sort of beginning of civilization. One of the first things that our species began to do of all the things that we do now is, I would say, is thinking of numbers and writing numbers. Even before writing words, etc., people would have started writing numbers because that is what they would need to record and convey to each other. The words could be communicated orally, etc., whereas the kind of information that numbers contain is sometimes better be recorded in some way, and so representing numbers is kind of one of the first tasks of mathematical nature, which was faced by the early people. So, this is just to give you a perspective. I'm going to talk about numbers as we look at them today. After that, I'll introduce what are called continued fraction expansions. Some of you might already know about them, but please bear with me for the introduction for the complete audience, full audience. Then I'll go over a historical perspective of that, how things developed about that. Then we'll talk to begin with. The title, as you may recall, is for continued fraction expansions for complex numbers. But to begin with, I'll recall various things about continued fraction expansions for real numbers. So our everyday kind of numbers. Even if you do not know what the formal definition of real numbers that mathematicians take, you certainly have a sense of what real numbers are. There are all kinds of magnitudes and sometimes they like representing debt or velocity in opposite direction. We will also introduce a negative number, a negative sign. So those are the real numbers, and we'll talk about continued fraction expansions for those numbers. These are some of the crucial things that crucial properties that I'll be talking about of these. Maybe I'll come to them when we actually get there. The next step will be to introduce continued fraction expansions for complex numbers. Now it turns out that there are certain intricacies in going from the real numbers to the complex numbers in this respect, and that has, while actually this topic has flourished for almost 300-400 years, continued fraction expansions for complex numbers have been relatively recent. Though even there, though actually they started towards the end of the 19th century, not much was done. Not much happened until say about last 40-50 years. So we'll come to that, and then I'll conclude with some concluding remarks. Okay, so now recall numbers come in various types. So you would know about integers, then like 1, 2, 3, 4, etc., and as well as the negatives, as well as the zero. I mean, zero is something that is crucial. It's kind of distinguished, and so let's start off from there. We know integers. Then rational numbers, also called fractions. They are numbers which are ratios of two integers, where the denominator obviously has to be not zero. So though the numbers of the form p by q, p divided by q with q not zero, are called fractions or rational numbers. Then apart from these, there are, as we all know, there are many more numbers that we need to talk about. And like, for instance, if you take square with which is 1 unit, both the side is 1, so the diagonal in that case is a number which as you know is the square root of 2, and that is not a rational number. You know that it cannot be expressed as a ratio of two integers, p by q, q not 0. So these numbers, they are irrational numbers. And well, apart from this example, I'm sure you would know many other examples as well. The number pi, the ratio of the circumference to the diameter, that is an irrational number. Then similarly, the number e, which is a celebrated number, that is also an irrational number, etc. And in fact, if you think in terms of the cardinality, how large the set of irrational numbers is, it is in fact much larger than the set of rational numbers itself. That's just to have in the background. Now the natural numbers, how do we write them? They are expressed as digital multiples of powers of 10. So here is a simple example. I need not dwell into detail about that. So this number 37,208, we write as 3 times the 10 power 4, etc. This expression would be very familiar to you. Now the negative numbers are denoted in a similar way, but you introduce a minus sign, and after that sign you take the negative of that original number that is positive. So then that's how you would express a negative number. The fractions are written in this same way, but there's also Yeah, so they are either written as P by Q, or is the more convenient way sometimes is simply to take the integer part and then write the remaining part like you would write 3 and 1 7. Now, apart from this, the you would know one more expression. This first part about irrational numbers, etc. I talked about, and then as they are not rationals, you would need something of a uniform notation for all of them, and that is served by what we use in the daily use are called the decimal expansions. So here the positive numbers are okay. So this is a decimal expansion of a complete positive number. Let's say you write the number is t. Then you write the integer part of it. This could be either 0 or a positive number. Then the second part represents the whether it is between so the range from 0 to 1 you divide into 10 parts and see how many parts are included in your number, and then correspondingly you write the digit for that. So as you will all be familiar, the number will then be written in this form. So and then that is actually written with a decimal point. And for the negative numbers, again there is a negative sign. So this is the expression for a number that is very familiar to us for last say 4 or 5 centuries. It's not much older than that. You should remember for the digits for natural numbers, the full numbers, the decimal expansion is considerably older, and India had a role in developing that to quite an extent, and so that goes back to about 2nd century or so. But the fractional parts being written in the decimal expansion is much later. It started with the Arabs, and then it got to Europe, and then it came to India. So the extended part took another route to reach us, and so it's a familiar object, however, in the last 3-4 centuries, and now it is everywhere used quite commonly. Okay, so in a similar way, like we expanded this number to in terms of 10 and writing this form, you know that you can also have binary expansions, where instead of dividing the next range into 10 parts, you divide simply into 2 parts. So, and you might have heard that this kind of thing, representation, is important in computer science. So where everything you would like to represent by 2 symbols which correspond to on-off symbols, and so 0 and 1. So in this, so like this binary expansion for every real number, I mean for this decimal expansion for every number, you would also be familiar with the binary expansion. Now there is yet another way of writing numbers, and that is what is going to interest us through the rest of the talk. But it has its own charm and its own uses, and perhaps maybe I mean, my own fond hope is that as time proceeds, the other systems, the system familiar to us. So here, the way I'm going to write this number R, real number, is as follows. I'll take A0 to be the largest integer less than or equal to t. Okay, I have the number t. Imagine a line, and you have a point of that which is represented by number t, real number t, and then you take look at the largest integer to the left of that in the usual convention, so or equivalently, which is less than or equal to t, and take this remainder. R1 is the remainder, t minus A0. And then naturally it is this R1 is between 0 and 1. Now if the R1 is 0, then I know that T is simply A naught, which is a very nice simple expression anyway. I don't need to do anything more about it. We'll stop there for that. But if R1 is greater than 0, what I do is put T1 equal to 1 over R1. Take the reciprocal of that. Okay. So there's a remainder, and then if the remainder is positive, I invert it and write it in the so T1 I write as 1 over R1. Now I do the same thing I did to begin with. So I take A1 to be the largest integer, less than or equal to this T1 that I have got hold of now, and write R2 as equal to T1 minus A1. Okay, now, so then again, I have 0 less than or equal, R2 is between 0 and 1. It could be 0 or can be strictly between 0 and 1. Notice that because this was obtained by inverting a number which was less than 1, this this T1 is necessarily bigger than or equal to 1, and therefore A1 is definitely bigger than or equal to 1. So this is here I'm putting a certain integer which is actually positive. So if R2 is equal to 0, then T is simply A naught plus 1 over A1. This is the standard form in which we normally write fractions as well. So this way I get, if at first stage I get this R2 equal to 0, now the picture looks exactly like our usual fractions. Now, so if this happens, we stop there. And if R2 is greater than 0, okay, take T2 equal to, follow the same formula, T2 equal to 1 over R2, and so on. So we repeat this procedure until, so what are the possibilities that can happen when we repeat this procedure? Either at some stage we hit 0, and it happened in the, for instance, R1 could be 0, maybe it never stops. It will, you will go on and on, in which case you will get a sequence. So there are two possible forms that will occur. So T will be equal to A naught plus 1 over A1, with here I have in the denominator A1 plus 1 over A2, and this A2 is not by itself, but plus 1 over A3, etc. This is what, this will be the result of of this procedure, assuming that at some stage the Rn, the remainder becomes 0, and this is your last term finished. So this is one possibility. T can be written in this way, or maybe it never stops, in which case you get a sequence. So A1 is T is A naught plus 1 over A1 plus 1 over A2 plus 1 over A3, etc. These are not plus to the original number, but every time the denominator is getting added. That is the way. So these are the two forms of continued fractions. Either these are finite continued fractions occurring here, coming here, or there is an infinite sequence which is arises out of this T. Now, of course, I just defined a sequence, but then this, what does the dot 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 mean? This dot 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 is something very similar to what you see in series. So when you write a series, you write, say, A1 plus A2 plus A3 plus dot dot dot. So in a series, so there's something which determines it, and you know that when you say the sum of an infinite thing, you mean that the series is convergent. So there's actually the values go to a particular limit, and the number that you're looking for stands precisely for that. So if you have for instance, if you're looking at a decimal expansion, 0. A1, A2, etc., AN, etc., the dot, if you write dot dot dot, it means that you know how the sequence is going to be defined, and with that definition, that corresponding series that we saw it actually converges to the original number. Now it needs a bit of proof, but not very difficult, that to see that when you have such an expansion, this also actually corresponds to, in a unique way, to this number D. So in the following sense. So in place of this sequence, let's say I stop at an and leave out the part after that, then I have here a certain rational number. This is a certain fraction, because I can convert back everything and I'll get a number which is a rational number. So this expression has built into it a sequence of rational numbers corresponding to what would happen if I truncate at n. Okay, so these are in fact called the convergence of that term, which I will come to later. And the sense of saying this is ... means that these rational numbers, the Pn by Qn, so up to n, let's say, corresponds to Pn by Qn, these numbers actually converge to T. So, and therefore this, like the decimal system, like the decimal representation of a fraction, this expression also uniquely represents this, stands for this. It provides the number an identity in the same way. In fact, here it's even a more intrinsic identity, because in the earlier case, 10 was an ad hoc base. I mean, you chose it for some reason. Or instead of 10, you could have chosen 8, you could have chosen 11, etc. But that was with a choice. Here, actually, once you think of the procedure, you actually have it gives you, takes you all the way to either it stops by itself or takes you all the way. So there's an intrinsic way of representing this number that is given by this procedure. Okay, now there are some simple facts here. It turns out that you will get this. We saw that, and it's easy to see that such an expression can be simplified to Pn by Qn, ratio of two integers, and conversely, it will turn out that it will stop if only if the number is a good old fraction, a rational number. If for every irrational number, this sequence is always going to go up to infinity. So this the sequence is either like A1, A2, AK, stopping somewhere, and or going up to infinity, and that happens precisely according to whether the number is rational or not. Sorry, I'm having some trouble manipulating this. These two following forms. So now let me come to a historical perspective on this. Though not quite in this same form, the procedure following such adopting such a procedure has been kind of has occurred even to some various ancient people, and in India this suppose many of you would be familiar with the term Shulva Sutras. In case you are not, let me just quickly recall that during the Vedic period, during the Vedas, there were performing yajnas, and in the course of that, the geometry was developed. They for the purpose of constructing the altars, etc. Which actually happened to be some in intricate shapes and so on, and various things like the Pythagoras theorem, etc. Were known at that time. And the thing in the present context, I want to recall that there is an expression there for square root of 2. Square root of 2 is important, has been important as the size of the diagonal of a square. So, and that they needed to have a measure of that in terms of the unit side as the unit. And then there is an expression which gives you 1 plus 1 by 3 plus 1 by, now here it is not added to the denominator, but I want to point out that what is done is that this remaining part you invert and then write a simple fraction for that. So it is going to be 1 by 3 is the 1 by 3 is the largest part that can be taken away of this form, which is what we were doing there. In the continued fraction expansions, we invert the whole thing, and but here only a certain convenient part is inverted, and the remaining part again is inverted. So there's a slight difference in the procedure, but there's a similar phenomenon taking place. At each stage, they take away whatever was covered and take the inverse of this thing. So you see that all of these are with 1 as the numerator, and the it's only the denominator that changes, just as we saw in this case every time. But here we have followed the process even further, where actually even this doesn't come up at all, but the denominator itself is inverted. So there is a certain similarity between the ideas. Again, in the process of the process for continued fraction expansion is intricately related to what you have studied as the Euclidean algorithm for finding the GCD of two integers. Remember, what you do is you successively subtract the smaller number from the bigger number. Given you want to find GCD of two numbers, you let's say positive, then you subtract the smaller number from the bigger one, so until you can, and then the other thing becomes smaller, you subtract back from the original. So this is what these steps correspond exactly to the continued fraction expansion, because the role is being inverted. Which you subtract is being inverted. It will be a good exercise to see the correspondence. I will not go more into that. The theory is of continued fractions for rationals is also found in the work of Narayan Pandita in the Indian tradition. Also, one of the things that we are going to say about continued fractional expansions is that when you are given a number, the expansion that you get, that you get, that I talked about, what happens when you the best approximations. So I just want to mention that moments has been used in the method by which they produce the panchangas, with the periodicity of the planetary motion, etc. One does the determination of time. In the process of that, Puttumana Somayaji is the Kerala mathematician who's in his work on Karana Paddhati, this method is used very effectively to simplify various computations. I don't think I'll have time to go into many more details, but this is just a historical input on the topic. Some more. Now, this theory of continued fraction expansions was in the form that I indicated. This was developed by Euler and Lagrange, some of the names, familiar mathematical names that you would have come across, who applied this to various problems. It is not something designed specially for any particular purpose that we see today, but there are many various results that came out of that. But in particular, there's something called the Pell's equation, consisting of finding integers xy, for which, so you look at this equation, x square equal to d times y square plus 1, where here d is some integer, positive integer, which is not a square. If it is a square, then you immediately things become a little specific, too special. We'll not go into that. But take a D which is not a square, and you want to find a solution for integers x and y for which this holds. I don't have to say positive because both of these are squares, so it wouldn't matter if you replace them by their negatives. And this was one of the important applications that Lagrange used, and that's where and that's how it picked up. The idea of continued fraction expansion picked up with that. So there is the Pell's equation. Now, though this part, what I'm going to say is not quite germane to the topic of continued fraction expansion itself. In this context, I should perhaps mention a few things here. That is, regarding this equation. First of all, for d equal to 2, the equation was studied already by the ancient Greeks. And their motivation in trying to, analyzing that was to get approximations for square root of 2. Notice that when you find such a solution, the ratio x by y is going to be very close to square root of d. Because these are going to be large numbers, then this is negligible. And so x square by y square is approximately d. And therefore x by y will be an approximation for square root of d, and that's what they were interested in doing for d equal to 2. This general equation was studied in India all the way from the time of Brahmagupta in his Brahma Sputa Siddhanta, and he solved such an equation for various values. Not only that, he introduced a method which could kind of which involves a bit of trial and error, but there is also an intrinsic theoretical part where we will not go into that. And that process actually in India from the time of Brahmagupta until the time of Bhaskaracharya, there seems a lot of people are likely to have treated this as a very important mathematical problem and worked on that, thought about it. In any case, it's found in many ancient manuscripts. And by around 10th, 11th century, a mathematician called Jayadeva came up, introduced a method. I have not written the name here. It is called the Chakravala method, by which by this equation can be solved for any d. I mean, he introduced a procedure by which turns out it gives a solution following the algorithm. It gives a solution, and in fact it turns out to be even more efficient than the continued fractions method. It corresponds to certain later methods in Europe, which are also efficient. And anyway, that's the short part of the story. On the other hand, of course, the continued fraction expansion, as I said, has a much wider applicability, and it's sort of considerably more elegant in various contexts. Now, what is Lagrange's name? You already mentioned to you in this context. So, and in the process of the theory, I mean, there's an important observation that he made, and that's sort of crucial to the theory. So, and that's about characterizing numbers which are solutions of this kind of equation. Now, we say that number t we call a quadratic number if it satisfies this equation. For some, there are some a, b, c integers for which ax square plus bx plus c equals 0, and we also this is a condition which will tell you that you cannot factorize this. If you can factorize it into rationals, then of course that's a different ball game. So these are, I'm taking a quadratic polynomial which cannot be factorized into linear factors, and x is a solution of that. Like square root of 2, if I square, that is equal to 1. So if for square root of 2, I'll get that the square of that. So a I can take to be 1 and c equal to -2. p equal to 0. So x square minus 2 equal to 0. Square root of 2 is something which satisfies x square minus 2 equal to 0, and that cannot be factorized into two linear factors with rational coefficients. So and that's precisely this is ensured by this condition. So yeah, and the Lagrange's theorem tells you that a number is quadratic if and only if its continued fraction expansion a1, a0, a1, etc. We recall that for each number now we have a continued fraction expansion, and this already tells you that what you are dealing with is not a rational number. So the continued fraction expansion is an infinite sequence. A0, a1, etc. It's an infinite sequence, and the theorem is that if the number is quadratic, then the sequence that you get is eventually periodic. Now, eventually periodic means that the same pattern is repeated. So if you have period p, which means that after that you will come back to the same original digit, so and repeat that. So that is periodic. Now, what is eventually periodic? Eventually periodic means that maybe there's some initial part which doesn't follow this pattern, but after some stage there is a periodic pattern. So that is the idea of eventually periodic, and written in words in mathematical form, what this means is that there is some m such that and some period p, there is an initial point m, and there is some period p such that for all n bigger than or equal to m, I have a of n plus p equals an. So that is the eventual periodicity with period p, and that eventuality starts with m. Yeah, so this parenthetical remark I already clarified to you. In particular, so we saw that square root of any number is going to be a quadratic number. So in particular, d as above has these have periodic. It should be eventually periodic continued fraction expansions. The solutions of the Pell's equation are described in terms of the entries of this continued fraction expansion. These in terms of these entries, there's a way of identifying what the solutions will be. So I'll not go into the details of that. Though it's not very difficult, it will take more time. So so the point is is to focus on this classification, understanding that a number, and now it's not just about square root of d, but here it is telling you something about the properties of numbers satisfying these kind of equations. A number is quadratic if and only if its expansion is eventually periodic. Now recall that a number is rational if and only if its continued fraction expansion is ends at some point, which means that the later ones are actually can be thought of as being 0. Whereas, and if it is 0, if it is eventually 0, then the number is rational. If it is eventually periodic, then the number is quadratic number. And it turns out that there are a whole variety of such correspondences that one can set up in terms of continued fraction expansions. Okay, so and here is one more instance, and this is something which is also related to some of my work. So I'll not be going into that, but the concept. So every number t, you know that every rational real number t can be approximated by rational numbers. In other words, for any t, there exists some p by q such that t minus p by q is less than epsilon. Given whatever epsilon, I can find p by q such that this difference t minus p by q is less than epsilon. Now, question of interest. We would like to know, given this epsilon, how large this maybe even to get small, this corresponds to a degree of approximation, the degree of error that you are going to allow. And to get a certain degree of accuracy, how many rational numbers, up to what denominator would I have to check or find? So this is one would like to interrelate this epsilon and the denominator. So question of interest is and a good choice. I mean, for computational purposes, you would like the denominator to be as small as possible, whereas on the other hand, I mean, how small a denominator. Of course, if you are going to be allow denominators say up to only 10, then the degree of accuracy that you can get is of course going to be limited. So you want to enhance your degree of accuracy that you want, but without having to go too high in the denominator q. Okay, so and this can mathematically this can be analyzed in terms of continued fraction expansions. So now let t be an irrational number, and suppose a naught a1, this is its the continued fraction expansion. Yeah, so this is something I already introduced. So if you take this a1 to an and write that is the corresponding number Rn as equal to Pn by Qn. These are called convergents of T, and as I mentioned, these as n tends to infinity, these converge to the number T. Rn converges to T, and we want to know how rapidly it converges. I mean, whether we can have control on the rate of convergence. It turns out that the best sequence of approximates that the Pn by Qns that we get for T, these are best approximates in the following sense. Suppose I start with any real number R, and so, and let this be its continued fraction expansion. By now you are familiar with it. So, and these are the convergents, weights convergents. Now take any fraction, a rational number p by q, q not equal to 0. Now how close it and look at how close it can be. And the assertion here is that if your rational number is such that it is closer to T than a particular convergent Pn by Qn, then that Q has to be greater than Qn. So in other words, if you take any rational number whose denominator is less than a particular Qn, then for that Q, you cannot have a rational number which is a better approximation than Qn by Qn. So it is a sense in which the Pn by Qn, the convergents, are the best approximates. And this is what I was referring to in the use when I talked of Karana Paddhati. Of course, Puttaman Samayaji was not did not involve any infinite continued fraction expansions, but a similar thing though holds for any even for finite expansions. So even if you had this truncated expansion, you can still get if you want to. This assertion is true even without this sequence being infinite. So even for a continued fraction expansion of a rational number, if you want the things of small denominator small, say if you have rational number which is say the denominator is of the order of 10 million, say 10 million plus 1, and you would like to have and the numerator is also huge and the denominator is also huge. You would like to have an approximation for that with something in smaller denominators. And so now see, there are in astronomical computations, there are certain factors by which you want to multiply, and now if that factor happens to be something with huge denominator and huge numerator, then instead of having to multiply by that number every time, you prefer to allow a certain error but have denominators which are smaller. So, and that's the purpose to which he uses this kind of fact, which is also true in as I said, in the finite case. Now, this also brings us to another related notion. So, for most, will not make sense, any precise, bring in any precise sense here, but it turns out that for most real numbers, you can have a rational number p by q such that this difference is less than delta by q square. Here, this is interrelating the denominator to the degree of error that is going to be allowed, and this can be achieved for whatever pre-assigned number. If I take any whatever pre-assigned number, then it's possible to have t minus have a rational number p by q such that this holds. Now, unfortunately, or maybe it's in the nature of things that this doesn't happen for all. That's why I had to say most. So, and the numbers for which this does happen, they are called well approximable. The number which is said to be badly approximable if that it is not well approximable. So that doesn't happen, which means that a number is badly approximable if there's some delta greater than 0, such that this difference of t minus p by q for whatever rational number you take, this difference exceeds delta by q square for all rational numbers pq. Such a number is called badly approximable, and these badly approximable numbers have played a very important role in many problems in number theory. And in a certain sense, for instance, one of the recent Fields medalists work, Lindenstrauss's work, for instance, is again related to these kind of numbers or problems involved with this. So, and there is not just an resolution. There are a whole variety of problems where this exceptional behavior of real numbers is something to be accounted for, and that is that comes in many problems. And so these are much talked about numbers, not necessarily in the original form, but variations of that, or more complicated variations of that, etc., etc. Here, of course, we are going to stick to the minimal manifestation of the phenomenon. These have attracted considerable attention, etc. Now, again, so this phenomenon again has a characterization in terms of continued fraction expansions, and it is quite simple. That a number t with a continued fraction expansion a1, a2, an, etc. is badly approximable if and only if this is a bounded sequence. So none of these. So there's some a such that all of these aj's are less than or equal to a. So notice that this is now you can see that why I said that for most. You don't expect this to happen. So this collection being bounded is a big constraint. So if I have to, you can imagine that if the sequences for which I have to limit myself to say entries less than or equal to 10, or even less than or equal to million, it's still a big constraint because there is a lot of numbers beyond that, and those have been excluded. So in that sense, but so this exceptionality turns out to be the same exceptionality under this correspondence. That is the point of this characterization. So let me again repeat what the characterization is. So a number t is badly approximable if and only if the continued fraction expansion, these entries are called partial quotients. So in the usual thing, there's only one quotient. So this sequence occurring in the continued fraction expansion, if this is bounded, then it is badly approximable, and conversely. Okay, so that is the background for the real numbers. Now I'm quickly going to say how this translates into complex numbers. First of all, even to begin with, there's a certain there's a bit of history. Uh, so A crucial difficulty is that, unlike in the case of real numbers, there is no natural choice. Recall that in the case of the real numbers, the largest integer less than or equal to that is a certain natural candidate for doing this kind of thing. However, now when you have a complex number, the same thing doesn't work. Let's say this is a box containing your number z, and it is between m plus ni, m plus 1 and plus ni, etc. You can follow this box. So each number z is going to be like the analog of the interval here is going to be this box. Now, not all of these numbers z are within I mean, there is no fixed choice that one can make, as we did in the case of real numbers. We took the left-hand endpoint as the natural choice. But if I try to subtract the just this part, then when I invert, so this number z this distance could be less than 1, because the maximum distance allowable here is square root of 2. So it can be, there are points here which are beyond that distance, and that will not be allowed. On the other hand, no matter which vertex you choose, there are points for which it will not be a good choice. So there is no canonical way of making such a choice. So, and that sort of begins the to make the crucial difference between the situations. Now, towards the end of 19th century, I think 1882 or something, Adolf Horowitz considered continuum fraction expansions, and what he did was to say that for each z, what you will do is to take the nearest integer. So for this z, you will take this. For z here, you will take this. For z here, in this part, you will take this, etc. So there's a certain nearer. So of course, there's a certain degree of ambiguity involved along these cutting lines here, but that's not anything crucial. You can make a convention that these I'm going to count there, and etc. So that's something that can be easily settled. So here is a complex plane. This is a typical z, and then the Horowitz algorithm corresponds to Horowitz recommends that you take this thing, and with this stipulation, he made various calculations and showed that you can actually write down a continuum fraction expansion analogous to the real case now, and it's no longer as easy as in the real case of real numbers, but he actually proved that these convergents, they did, first of all, first thing they had to make sure that these denominators actually go to infinity, and even that needs some work, and then that the convergents, the analogs of what you would write, that is, you truncate, you get the sequence by following this procedure, and truncate it at the nth stage, that will be your Pn by Qn, and that converges to Z. And not only that, he then proved that the analog of Lagrange's theorem also holds in this case. So if you take a complex number which satisfies a quadratic equation with these complex integer coefficients, then the number is quadratic if and only if the continuum fraction expansion is eventually periodic. Now, the algorithm that we described, this is now called the Horowitz algorithm. Now, I mentioned about the Lagrange theorem, but Horowitz himself did not go into the get to the approximation properties. That was something which was done in the middle of last century, so by David Hensley. So in the present case, actually, there is no correct analog of the best approximation property. What one gets is something of a weaker assertion, which is which tells you that the convergents are reasonable approximations. They may not be best, but they are reasonable approximations, in the sense that if you take another fraction, now these are complex integers, another fraction, and then it can be this difference can be less than this thing, even with q less than qn, but nevertheless it can be less only by a certain fixed factor, and for many purposes you can and this factor can actually be computed, and you know what it is, and therefore the certain handle, and one knows in a certain sense that they are reasonable approximations, though they need not be best approximations. Interestingly, what is the way in which you can get a best approximation is still an unsolved problem for complex numbers. One doesn't know how to go about so that you can or whether at all it will be possible. That one cannot say. Now there is also a characterization of badly approximable numbers, and having got hold of this weaker approximation property, you could still conclude that in this case also the number is badly approximable if and only if the continued fraction expansion involves only bounded collection of numbers. So here is another remark that in the case of complex, in the case of real numbers, there is only one way of realizing integers. You have to have 1 and then 1, 2, 3, etc. And then there is no. On the other hand, in the case of complex numbers, there are more ways of realizing numbers. Thinking of integers. Now, those of you who may have learned some algebraic number theory would know that there are rings of integers and various subrings. What are called subrings behave like the integers in this case. And the question we would also ask is whether, and here of course I sort of directly assumed that we are taking integers to be complex integers to be those for which the real and imaginary parts are integers. That's what one would naturally think about. But there are other ways which I'll not spend time on at this time. So, and there are 5 such continued fraction expansions of 5 such rings of integers. They correspond to for those of you who are who would know some algebraic geometry. There are 5 Euclidean domains, and for that the continued fraction expansions can be defined, and the analogs of Horowitz and Hensley were worked out by a German mathematician called Leckheim. So we know that in that generality as well. Now let's as we saw, there are some lacunae for the continued expansions so far. So now there are some observations that I want to. I noticed an interesting phenomenon about these. So actually, so here there is a difficulty about where you choose, etc. But interestingly, it doesn't matter which one you choose, so long as you choose one which is within distance 1 and go even arbitrarily, which is so this is why it is referred to as lazy choice. You do not want to worry about which one is the closest, and simply find one and get hold of it and write the continued fraction expansion. The initial feeling would have been that no, in that case the things may not converge, but it turns out, and it's a curious fact of life, that in that case also the continued fraction expansions, they converge to the appropriate number that you want. So this is something just one can keep in the background. It's not that these expansions one may hope to use for any concrete purpose, because the convergence, though it is guaranteed, it may be very slow, etc. So unless we know more about it, we cannot say how to use it. But nevertheless, it's something good to keep in mind that that is such a flexibility available, and if you can make certain choices cleverly, then perhaps you can get hold of what you want. And there are some curious examples in which you can even use just a finite set of integers to write continued fraction expansions. Now, though that lazy choice exists, it doesn't lead you very far, but there is another possibility, namely that instead of the Horowitz algorithm, the fixed algorithm, you can think of using alternative possible algorithms. You're going to follow a certain rule algorithm. Each time you're going to follow the same rule, but that rule need not be that you choose the nearest one, but maybe under certain conditions you might choose let's say the left hand endpoint. You insist on choosing the left hand endpoint, or choose something for which this is something that does appear, that where the sum of the real and imaginary parts is even, or things like that. So myself and collaborator of mine, Arnaldo Noguera, we have been interested in this problem, and so well, we studied the continued fraction expansion with respect to a large class of algorithms, and we found some algorithms which have certain advantages over the Horowitz algorithm. One of the lacuna for Horowitz algorithm that bothered us was that so for each number you have a certain sequence. Now, in the case of real numbers, it is easy to see that is also the converse. Given a sequence, you can always get back a certain number. But it turns out that in the case of the Horowitz algorithm, if you look at the collection of all sequences, it doesn't have it as neat a structure, and you cannot say which sequence I can get back to, from which sequence I can get back a number. And we introduce certain algorithms for which this can actually be done. So there is a one-one correspondence in that case. For each number there can be more expansions, but what I'm saying is that for each number there is a certain sequence from a fixed set of sequences that you can assign, and from that fixed set of sequences you can get, for each of those you can get a number. So this is a very somewhat useful situation in certain applications, etc. And and sort of describes a certain set of conditions for which this necessarily happens. And more recently, in a paper with my student Ojas Sahasrabudhe, we studied continued fraction expansions with this certain general algorithms. So the process of picking an algorithm can be described very simply. It's just a function which is to tell you which integer you should assign for every number. But the thing is, for that algorithm to give you good properties, there are certain natural conditions that are needed, and we analyze those conditions, describe those conditions under which various interesting properties that we saw, like Lagrange's theorem and characterization of the best approximation property, or the characterization of badly approximable numbers, etc. These hold. I'll not go into more details, but it turns out that there's a lot of flexibility that is allowable to us in matters of this picking continued fraction expansions, and with future research, hopefully it will sort of lead to many more insights. That is the hope. Now, I just want to, before I conclude, I want to point out that it's at some point, I mean, say if you go back 200, 300 years back, then the series that we now the concept of series, or that we now take for granted, was something of a big thing. So people were talking about convergence criteria, Allahabad, and so on, and which series converge, and series expansions, etc. So, but now we have gotten over the difficulties of with regard to the convergence issues, this, that, in various ways, and are able to use successfully the idea of series. Now, in a sort of philosophical way, one can expect that same thing could develop for these expansions in future. Now, I have another comment I want to make is that I have not gone into applications for computations, etc., except for mentioning some historical things. and partly because that's not my expertise, but I'd like to mention that there is a considerable amount of literature in using continued fraction expansions for computational purposes, etc. So with this, I'll conclude with thank you for your attention.
Thank you. Thank you very much, sir. Although we are just short of time, but there are a few questions. I'll take up those questions one by one.
Okay.
So the first one is how to solve a cubic equation by Vedic mathematics.
How to solve using what?
Cubic equation by Vedic mathematics.
That's not my subject. So
Okay.
Vedic mathematics is not something which I talk
Okay.
about, and yeah.
Okay, I'll take up the next one. Is Lagrange theorem applied in complex equations also?
Yeah.
Okay.
For so Lagrange's theorem is about the number and its corresponding. Now the continued fraction expansions themselves depend on how you arrived at them. The earlier results were for expansions with respect to the Horowitz algorithm, or in the real case the classical algorithm, etc. Whereas now we have a more general notion of algorithm, and in that context also, when you take the new algorithm and the for each number and look at the corresponding associated continued fraction expansion, the same correspondence holds. The number is quadratic if and only if the expansion is eventually periodic.
Okay, the next question is by Riddhi Mishra, but I think I'm not able to clearly understand the question. So I'll ask Riddhi Mishra.
Sorry?
Yeah, Riddhi, can you unmute yourself and can you ask your question? Riddhi Mishra. I think she's not here. She's asking that is there any relationship between P and Pn, and what is fixed factor?
Oh, what is fixed factor? So there is a certain constant which one can compute. Depending on the algorithm, there's a certain constant that one can depend and on the number. There's a certain constant, so such that the let me go back to that. So you are comparing these say z minus p by q with z minus pn by qn, right? And this you are doing for here. There are various things that could be changing. One is the number z that I'm not changing. For a fixed number z, I'm looking at the these how this sequence approximates z, the pn by qn, and how an arbitrary p by q approximates this. Now, in the good case, in the real case, in the case of real numbers, you know that this is necessarily better. This is bigger than or equal to this, right? And the same thing we want to say is bigger than, not necessarily bigger than or equal to this, but there will be a constant, say like half. Depending on the number, there will be some constant, so that this is bigger than or equal to, this is less, sorry. Okay, since I'm thinking of in terms of this rather than this, so this we're saying in the good expected, what you would want or expect, and that holds in the real case, is that this is less than or equal to this. So the fixed factor means that you can get a certain constant, so maybe 5, maybe 10, or maybe a million. It doesn't matter. But there is a certain, depending on the data, there is a certain constant, such that each of these is less than or equal to that particular constant times this for every z, every q for which the less than or equal to, for every q which is less than or equal to qn in absolute value. Is this clear what I'm saying?
Yeah, I hope so. I have just received a response, yes. Okay, thank you. Thank you very much, Professor Dani, for such an
Thank you.
exhilarating and enlightening talk for nearly it lasted for about an hour. And on behalf of the organizers, that is the three science academies and the host institution, that is the Dayal Upadhyaya College, I would like to thank you and